In this presentation, we will introduce a new device called a superconducting power filter. We will study its applicability to high-voltage direct current grids. We consider a two-terminal 800 MW HVDC link. The parameters are taken from a benchmark defined by the C-grade before group in the technical brochure 604. To decrease the stability of the system, we modified the length of the DC line from 200 km to 250 km. The stability of the system can be analyzed by considering the Jacobian matrix of the equivalent circuit of the positive pole. The voltage source models the converter CMA1 operating in VDC-Q mode. The current source models the converter CMC1 operating in PQ mode. An approximate expression of the stability condition is recalled here. In practice, the control loops modify the dynamics of the system. This makes it difficult to calculate precisely the stability limit. But this expression is useful to illustrate that when the power increases, the system becomes unstable. For this case study, the stability limit is found to be equal to approximately 350 MW per pole. Let's see what happens under and above this value. At 300 MW, after a transient, the voltage of the DC bus is constant. The CSM is stable. At 400 MW, both the DC voltage and DC current oscillate. The system is unstable. To increase the stability limit, we propose a new device called superconducting power filter. This is a non-inductive superconducting coil. The double spiral winding is used to reduce the inductance. The superconductor behaves as a current-dependent resistance. When the current is low, the resistance is zero. Around or above the critical current, the resistance increases. Actually, we must account for the temperature. This is why we use a thermo-electric lump parameter model in the following simulations. The superconducting power filter is connected in series with the positive and the negative poles. The device critical current is designed to be equal to the current around the stability limit. As a result, when the power increases above the stability limit, the current increases above the critical current, and the device becomes resistive. In the first approximation, the resistance of the superconducting power filter adds to the resistance of the pole. The stability limit becomes higher. Let's see what happens for our test case. At 300 MW, the system is still stable. Note that because the DC current stays below the device critical current, the device resistance is zero. At 400 MW, the system that was unstable before is now stable. The DC current increases above the device critical current. As a result, the device resistance increases, thus pushing back the stability limit. Note that when the power decreases, in few milliseconds, the superconductor temperature falls back and the resistivity goes back to zero. We are now working towards an experimental proof of concept. This is a photo of the DC test bench installed in our laboratory. By increasing the power above 1300 watts, we were able to observe the instability. We built several superconducting power filter prototypes. On the left, this is a photo of a device made of 2 meters of Repco. On the right, this is a device made of 5 meters of Bisco. The measurement of the I-V curve shows that the superconductor was not damaged during winding. The next step is to insert the superconducting power filter in the DC test bench and to see if the device improves the stability.